let's start with a question. What is the maximum number of nodes that we can have in a single OpenSearch cluster?
Any guesses?
OK. What is the maximum number of shards that we can allocate in a single OpenSearch cluster?
800. 75K. OK, what else? OK, that's encouraging.
Awesome. Yeah, like I heard answers like such as like hundreds, 400, thousands, and so on. That kind of makes OpenSearch limited, right? So we can only scale so much to so much of nodes or so much of shards in OpenSearch. But we are here to talk about how we can make OpenSearch truly limitless, like how we can truly infinitely scale. I am Prabhakar. I am a principal engineer in Amazon OpenSearch service. I'm also a contributor in the OpenSearch project.
Hi, I'm Shweta. I'm also principal engineer with the Amazon OpenSearch service team, and I'm a contributor and a maintainer with the open source project. OK, let's get started. OK, so before we get into the scaling challenges or the limits that we just spoke of, right, let's look into an OpenSearch cluster. So in an OpenSearch cluster, we have nodes with different roles. So we have data node, coordinator, cluster manager, right? So let's take an example. Let's say you want to ingest some data and search on it. So the first thing you do is you create a cluster, and then you create an index, right? An OpenSearch index is partitioned into shards. So now, in this example, right, let's say you set 3 shards, because we have 3 data nodes in the cluster, so we have 3 shards. So each shard will get assigned to one of the data nodes. And you're all set. So you'll start your ingestion and search traffic, and the request will go to the coordinator node, and the coordinator node knows which shard is assigned to which node. So it's able to route the request accordingly, right? And then comes the cluster manager node. So think of cluster manager like a brain of your cluster, right? It manages the cluster for you. So it's like, it provides a consistent view of the cluster, because we all know OpenSearch is a distributed system, right? Like data nodes are running independent of each other. So there's no single authority among the data nodes to give you a consistent view. So the cluster manager provides that consistent view. Right? So with this, right, so we saw, previously, right, we created one index, we ingest data in it, and we searched the data. Now let's say you have more data. You'll create one more index. Let's say more data, you'll create one more, and so on, right? You'll keep on creating more and more indices, and then they will have more and more shards. And then if, let's say, 3 data nodes were not enough, we will add more data nodes also, right? We'll keep on adding data nodes. So looks like OpenSearch is designed to scale horizontally, right? Like it is designed to scale. So why doesn't it scale, right? So there are certain components in OpenSearch. So we'll go over them one by one, and we'll look at the bottlenecks and how we are solving, and which can help us truly scale OpenSearch to limitless, right? Without talking about any limits or numbers, right? Where someone said 100 nodes or 70,000 shards or 1,000 shards, right? Can we break free from these limits? OK, so one of the first component that I want to pick and talk here is the cluster manager. So we just briefly spoke, right? Like the cluster manager is like the brain of your cluster. It's managing the cluster for you, right? So let's take a look at its responsibilities. So it maintains the cluster state for you. So like we were saying before, right? Like you first create an index. So anytime you create an index, you delete it, you update its fields, any operation that you do, right? It's like it happens through cluster state. All that information, it's like the metadata of your cluster, right? The actual data is what you're ingesting or what you're searching, but it is the metadata about your data, right? And it is stored in the cluster state. And the cluster manager node manages the cluster state for you. And then we saw, right, we have nodes, like an OpenSearch cluster is made of nodes. Like we have one or more nodes in the cluster. So when a node joins the cluster or it leaves the cluster, right, it is all handled by the cluster manager node, so that we always have a consistent view on which nodes are part of the cluster and which are not in the cluster, right? So another thing, right, as we briefly touched upon the shards earlier, right, like where we are saying, OK, the coordinator node knows which shard is assigned to which node. So where is that information stored? That information is again stored in the cluster state, right? And then there's a component called shard manager, which inside of cluster manager handles all the responsibilities with managing shards. And then there are certain admin APIs. I think once, if you guys are using OpenSearch, you would definitely would have used cat APIs, cluster stats APIs, node stats, right? So these are some of these APIs are served by cluster manager node directly. And then snapshots. I don't think anybody here who has an organization who is running a production workload would not have taken a snapshot, because we all know nodes go down, like machines go down, right? And data can get corrupted. So we keep on taking these backups so that if any situation arises, we are able to restore and get to a deterministic state, right? And then few other things, like few other responsibility the cluster manager node has in terms of election, because normally when we create a cluster, we have 3, it's a recommended, right? You keep 3 cluster manager nodes. So in case one goes down, other one can take over. So now there's an election process so that the next node can get elected as the leader. And then there are health checks, right? Because the cluster manager node has to provide that consistent view. So it keeps on doing these health checks with every other node in the cluster. So it knows if a node is not responding, it can figure that out and remove that node from the cluster, right? So this was just few key responsibilities of cluster manager. With this, right, let's move on. So as we saw, right, our cluster manager node is an all-rounder. It does so many things. Even though it is not in our indexing and search path, still it has so many responsibilities. And the scary part is, right, like let's say if one data node goes down, it's okay, your cluster keeps on operating, you keep on ingesting and searching. But if your cluster manager node goes down, your cluster goes down. So its availability becomes even more critical, right? Because it can become a single point of failure for us. Then the only option users have, right, today, if your cluster manager node is overloaded, is to scale up. You can add more memory, you can add more CPU, but then there are still ceilings to it, right? How much you can scale up. So at some point, you will hit some limits there, and you won't be able to scale further. Then what is the solution? Then obvious thing that comes to our mind is horizontally partitioning, right? Like scale horizontally. And in context of cluster manager, then that becomes is, can we reduce the work the cluster manager node is doing? Can we distribute the work it is doing to other nodes in the cluster, right? And take their help to reduce its responsibilities. Because if we reduce the work it is doing, then there is less, it'll run more stable, it'll be more scalable, right? And then we'll have lesser issues, and it'll not be a single point of failure for us. So with this, right, that's the obvious question on everyone's mind, right? Like, can we make it lean? Can we remove certain of its responsibilities, right? So when we were going through the list of responsibilities for cluster manager, the first responsibility that we had was the cluster state management. So before we talk about any bottlenecks or optimizations, right, let's look at how does a cluster state look like, the objects it has, right? So the first thing we spoke of is it has your indices. So let's take an example of a time series index, right? So today is 26th. So let's say you create an index for 26, 0, 24. You'll ingest today's data in there. And then for tomorrow, you'll create another index for 27, 20th, and so on. So let's say you keep 30 days of data. So you would create 30 indices. And the information for all the 30 indices is stored in your cluster state, like their settings, the mappings. Mappings is essentially the fields in your index and their types, right? Is it a long, it's a string, keyword, and so on, right? And then if there are any aliases pointing to that index, right, all that information is there in the cluster state. And then we just spoke about, right, like the coordinator node has the mapping of which shard is assigned to which node. So that information is stored in a data structure called routing table. So if you look at the screen, right, like so it'll say, okay, there's a shard for that index, and for the shard 0, right, it is assigned to a node ID. And which node ID, right? So this, essentially think of it like a map, right? You have that key as a shard ID and the value as a map. So in the previous example, right, like when we were creating the time series indices, let's say we kept 30 days worth of data. So we created 30 indices. Now each index had 5 shards. So now it becomes 150 shards. So all that information of all those 150 shards stays in this routing table that we have. Right? And then we were talking about cluster manager node handling membership changes, like any time a node joins or leaves the cluster, it's all part of the cluster state. And then we have certain settings at the cluster level, and there are few other entities that we have in the cluster state, like templates, snapshots we briefly spoke of, custom objects, and so on, right? Like these are all the entities which are stored in the cluster state. So it's a one big jumbo object which has all your metadata. Right? So now, so what's the problem? So far, so good, right? Yeah, it has it, so what's the issue? It can manage it. Yeah, I think the interesting bit is, like, it has to, like, every time you create more indices and more shards, right, it goes into that one big jumbo object that we are maintaining. And at certain point, that object will not scale beyond a certain point. Let's take an example, right? So we are talking about 30 indices, all good. But let's say you have petabyte worth of data, and you may end up creating tens and thousands of indices. And that can have your maybe a few hundreds and thousands of shards, right? Like 100K shards or 200K shards. You may want to create that many. And all that information is stored in that one big cluster state object, right? And just to think of the scale of the problem, right, where it goes exponential is, now every time your cluster state changes, the cluster manager node has the responsibility of publishing the state to every other node in the cluster. So we had in the beginning, right, we had a 3-node example. Like we had 3 data nodes. It's pretty easy. Let's say my cluster state is 10 MB. Okay? And then there are only 3 data nodes, so it's only 30 MB worth of data it has to send over the local transport to all the other nodes. No issues, right? It'll send it, no problem. Now think of it, you have 1,000 nodes in the cluster. That same 10 MB state now has to be sent to 1,000 nodes in the cluster, and it becomes 1 GB of data that 10 GB, sorry, of data that we are talking about to send it to the 1,000 nodes in the cluster, right? So that's where the problem becomes exponential, right? In a steady state, OpenSearch is smart. It sends only diffs. It does not send the full state every time there is a state change. Let's say you create an index, you delete an index, right? We send the differential state only. But think of situations when there are node drops, or we are doing blue-green deployments, and any point in time when there are more nodes joining at the same time, right? That's when it stresses the cluster manager node. And its memory shoots up and all that, right? Like its CPU spikes, and we have a problem, right? So now, how do we solve this? So as we were discussing earlier briefly, right, can we reduce its responsibility, right? So as part of cluster state, right, now we know it does 2 things. It does processing, it does publishing. So the processing we cannot take away, because otherwise it will become inconsistent, right? Like there should be a single authority, because we all know cluster state is a big jumbo object. So we can process, like one node can take the responsibility of updating it, but can we offload the responsibility of publishing to the other nodes, right? So let's see how we can do that, right? Let's look at the solution. So the first thing that we are doing right now is, as we speak, it's getting implemented in OpenSearch, is the remote state cluster publication. So essentially what happens is, the cluster manager node will just inform all the other nodes in the cluster that new state is available. And all the other nodes will just download it from the remote directly, instead of sending over the local transport to every other node. And what it gives us is 2 things, right? 1, it reduces the overhead on the cluster manager node for publication, no overhead. And 2, now that the number of data nodes can be added to the cluster independent of the cluster manager node size. We don't care if it is running a 8 GB memory master or 32 GB, right? We don't care, because it does not have that overhead so that the factor of the number of nodes goes away, right? We remove that from the equation. And then the another beauty of this, right? Like now that we publish it to remote, earlier the full state object, either you get everything or you get nothing. That kind of a mode, right? Like because cluster state is a big object. But the way we are storing it in remote, each granular entity is stored separately. And now a node can make a decision that on demand what data it needs, instead of downloading everything, right? Instead of downloading the full 10 MB of the state. So let's say, the same example, right? We have data node 1, and let's say it only has 10 shards assigned. So ideally, it cares about the index metadata for those 10 shards, even though if we have, let's say, 1,000 indices in the cluster. It doesn't care about that other 990 indices. It doesn't care. It doesn't need to download. Similarly, for its routing table also, as we were looking before, right? It only cares about the shard routings, the primary and the replica for that assigned to that node, right? It doesn't care about the other. So now it can just download things on demand. And the data that it needs is only a subset instead of everything. Yeah, and the other thing is, right, so for coordinator nodes, right, that's the coordinator, so where the coordinator nodes, like dedicated coordinator nodes help is, because if you have, for the coordinator node, we know, right, coordinator node's responsibility is to route the request. So it needs a full view of the routing table. But then if it is, like the data node is doing double timing, it is acting as a data node also and coordinator, it cannot have that optimization. But what if we segregate them? Like there is a separate coordinator node and a data node. So data node can download subset of the information it cares. Coordinator node needs the full view of the routing table for the shard routing. It can download it. But then the good part is, now the coordinator node does not need any index metadata because it is not the one doing actual ingestion and search. So that's again a win-win. So they do only limited amount of work, right? So yeah.
We just learned about how we can optimize on the shard routing, like between the coordinator nodes and the data nodes. And let's talk about shard manager, which is the creator of the routing table. So shard manager does two actions primarily. The first one is allocation. Let's take this example of the cluster with 3 nodes. So you create an index with three shards. It is the responsibility of the shard manager to assign these shards to these nodes, like say shard 0 to node 1, shard 1 to node 2, and shard 2 to node 3. And the other action it does is the balancing. So let's take an example of a 10-node cluster where you have, like, say, 500 shards spread across the data nodes. So when, say, these shards belong to 2 indices, and when you delete an index, like some of the shards like gets deleted, the shards belonging to the index gets deleted. That means like some of the nodes may become empty. So it is the responsibility of the shard manager to reallocate those shards. Say, for example, from node 1, which has 10 shards, to node 10, which has 0 shards. It's a responsibility of the shard manager to move the shards between the nodes and keep it balanced all the time. It seems like a simple work, right? You know, just assignment, like some shards, some nodes, like just assign it, right? But why does it become a bottleneck? When the number of nodes or the shards is really less, when you're talking about 10 shards or 5 shards, like and 100 nodes, it becomes simpler. But if we really talk about the scale of, say, 500 nodes, 1,000 nodes, and million shards, this problem becomes really complex. Just going back with an example, say you have a 500 node cluster and you create an index with 1,000 shards. So what happens is, for every shard, it goes and finds which is the right node to allocate. That means, like, so for each of the 1,000 shards, it goes to every node and see if I can allocate this shard on this node. That makes us 500,000 decisions it has to make. It has to go through 500,000 loops and make the decision. Similarly, when in the same 500 node cluster, say one of the node drops, and that means like the 1,000 shards that's assigned to the node becomes unassigned. So OpenSearch now need to allocate these shards to a different set of nodes. And similarly, like it's going to do this 1,000 unassigned shards into 499 remaining nodes. So it's going to do 499,000 computations. And this is like really expensive. And how can we solve it? So instead of doing this one shard calculations where we can see if it can be assigned to a certain node, we can batch all the shards that has to be assigned and see what is the right node it has to be assigned. So in this case, we can eliminate, instead of doing this 499,000 computations or 500,000 computation, we can just do 500 computations, like one per node, and see if all the shards can be assigned to different nodes. Does it solve the problem? Yes, to some extent. But the number of nodes is still becoming a problem. Like if you really have a large number of nodes, say 1,000 nodes or 5,000 nodes in your cluster, it still is a problem. So the one way we can eliminate is by introducing a logical concept called pods. These pods are like very similar to cells, like that we call it in the distributed systems. So you can split your cluster into multiple different pods, and you can assign shards to certain pods. For example, you can say my index 1 goes to pod number 1, my index 2 goes to pod number 2, my index 3 goes to pod number 3. And this could be like very common in the log analytics use case where you have like multiple systems in your organization using one single cluster. Then you can say, like, my application 1 uses pod 1, my application 2 uses pod 2, and so on. That way, the number of nodes in a pod is always limited, and the allocations will be on the inside number of nodes inside the pod, which is always limited. As we scale up, we will keep introducing new pods, but keeping the problem still simple to a pod. And we talked about like the allocation and the balancing bottlenecks, but there is like a variation to the balancing bottleneck. For example, like as your organization has multiple like applications which uses OpenSearch cluster, there could be one application which generates terabytes of logs. There could be another application which could be generating MBs of logs. And you could have designed your application in such a way that like, everything is 10 shards. So what happens is like you have certain shards which are really big in size and certain shards which are really small in size. So these big shards can end up in the same nodes, and those shards become the hard shards, and it kind of impacts your search latency. To avoid this problem, we are working on a shard balancer, which is like looking into the heat of the system, heat of the shard. The heat of the shard is primarily on the 4 factors. The 4 factors are the CPU, like what is the CPU utilization that it has, the memory utilization, the disk occupancy, and the disk IOPS. So instead of doing the shard count and the disk usage-based management, the shard balancer also look into the heat of the shard. So it is very much possible that you have 2 nodes, one has 10 shards and the other node has 2 shards, but they have like same amount of CPU utilization and the memory utilization. So like we kind of looked into like how the different application we can manage it, but it is common in search use cases where you use a routing ID. So you have like 200 shards, and you use something called as a routing ID so that the request always goes to a particular shard. So what happens is like sometimes like some of this shards becomes hot because like a lot of users are using one particular routing ID, and that becomes hot. And whatever however we move the shards to a different node, it still becomes hot because like this is the hottest shard in the entire system. So whichever node which was the shard becomes the hot. To avoid this problem, we are working on online shard splitting so that we can split the shard which is hot into multiple smaller shards. That way the resources spread across different nodes. We do have like splitting APIs today. We have split shard API and reindex API, but that always operates on the entire index. So if you have 10 shards, you can always split it into 20 shards. But with this reindex API, with the online shard split, you can just operate on the particular shard. For example, the same example, out of the 10 shards, only one shard has the hot, then that particular shard can be broken into 2 or 3 smaller shards. And when we do this, there is no downtime. The read and write traffic can go into the shards. So we talked about like the shard assignments and how can we balance the cluster. The actual problem comes when when the requests are actually used in the cluster. So like picking an example, this 500 node cluster, where you have a request like say you have one index that goes to 500 shards. Then this entire request, like one bulk request containing say 10,000 documents, has to be split into 500 shards and sent to each of the shards. And as the number of node grows or the number of shard goes, this becomes a bottleneck. One of the ways we can do is instead of sending a request at a shard level, we can send it at a node level. So that means if this 500 shards are allocated in the 200 nodes, instead of sending 500 requests, we can send 200 bulk requests internally. That's one of the optimization. But still, it kind of goes back to the node. From the shard, we moved the problem to a node level, but that doesn't completely solve the problem. One other way to optimize is like round robin the request. So we know like this request has to go to all the shards. So instead of sending the request to different shards, we can round robin. The first request goes to shard 0, the second request goes to shard 1, the third request goes to shard 3, and so on. That way, the request can just be sent to a shard level, and overall, eventually, all the shards will have like equal amount of data. We also looked into like how pods can simplify the issue. Like so, similarly, the request fan out can also be solved with the pods. So the request can only be sent to the nodes inside a pod. But with pods also, like eventually we can have like a lot of pods. We can have like 100 pods in the cluster, but that means the coordinators still need to understand all the 100 nodes, all the 100 pods. One way to solve that is hierarchical coordination. So instead of having a coordinated layer separate outside the pods, we'll have a coordinated layer inside each pod. So the outside coordinator layer just understands which pod I need to send to, and the coordinator inside the pod understands which node the request has to send to. That way we'll be able to scale infinitely. As the number of nodes grow, we'll keep adding pods, and the coordinator outside will just need to know about the pod in which it is sent to. And eventually, if we even grow the number of coordinators, we can have another level of coordinators, so we can have multiple levels of coordinators and scale infinitely.
So there are other enhancements that we are looking for the admin APIs. So we briefly touched upon the admin APIs, right, when we spoke of the cluster manager responsibilities. See, one of the challenge, like as the cluster grows, right, with more number of nodes and more number of shards is, like these APIs tend to become very expensive. Now, let's take an example of cat shards, right? See, when you have only, we were talking about 30 indices with 5 shards, right? It's just 150 shards. It's all fine, right? Like the cat shard API works very smoothly. But the moment you have, let's say, 100K or 500K shards, like the Prabha was talking about, right? Then that's when, right, the API will never return a response. It will just time out, always, right? Because it has to do so much compute. So, right, some of the improvements that we are looking for most of the admin APIs around our cancellation support, pagination for those APIs, right? And then we have another set of APIs, like node stats, indices stats. So these stats APIs give stats, and they're very useful, right? Because you can look at the performance of your cluster, how it's doing in terms of ingestion rate, search rate. All those metrics are actually generated through these stats APIs, right? Now the problem is, these stats APIs, from the data node, right? So what happens is request comes to a node, right? And that node will ask, it's a broadcast request, it will ask every other data node in the cluster to send the stats for the shards assigned to that node. And the problem today is all the nodes send these stats at a shard level. Now, if we have 500K shards in the cluster, we are getting those 500K stats objects. And then the coordinator node, or the node which is serving the request, right, the user request, is actually going to aggregate everything and create a summarized view and send a response out. And it becomes really expensive in terms of memory and CPU on that node, right? And with 500K, I don't think the request will ever come back. So what we are looking at is, like, can we pre-compute those stats on the nodes, on the data node itself, an index view and overall view, and just send it to the coordinator so that its work is very minimal. Just aggregate the response and send it out, right? So, and few other optimizations that we are looking at in terms of adding admission control for CPU. If CPU is running high, reject the requests, don't even get them in. More aggressive filtering, like the default API should return a minimal response. And then if you need something, any specific stat, you add it in the request params, right? Instead of just giving everything by default, spewing of GBs of data for large clusters. And then the another optimization that we are looking at is the read APIs. Today, some of the read APIs are only served by the cluster manager node. So we are looking into whether other data nodes, again, distribute the work, right? Can other data nodes serve those requests directly? As long as they have the latest cluster state, right, they are capable of serving that request. So why not use them and be able to distribute the work? If you have a 1,000-node cluster, distribute that work to 1,000 nodes instead of a single cluster manager doing it. Right? So, and also we are looking into some optimizations on the snapshot APIs, because again, the same challenge exists with snapshot also, because when you take a snapshot, you have to go and touch every shard in your cluster to take a snapshot. And again, it doesn't scale. So we are looking into optimizations on the snapshot side. And with this.
Yeah, these are some of the items that we are currently working on, which will help us to scale better. Like we are working on the storage optimizations, like, for snapshots, we use any remote storage, remote blob store, and that, like, when you have like more thousands of nodes in the cluster, like everything during the snapshots, all the data is going to be pushed to the blob store, and that's good. Like, and we'll save throttling. So those are some of the areas, and also we are looking into how can we separate the reader writer. So today, like the same data node does the both indexing and the search work. So can we separate them so that you can have different number of nodes for readers and different number of nodes for writers? And stateless cluster manager. Can we really make cluster managers, instead of having 3 nodes, can we make 1 node and make it truly stateless? Thank you.
Yeah, thank you.